Hello juniors, today we're going to see electronic assignment 43, which is using logarithms to solve equations. We're going to do some examples together in order to see how to apply all of the different properties, all of the different laws of logarithms that we have learned in the previous classes in order to solve equations. So it says, apply graphing skills and solve equations that relate to real life situations. Okay, so for the first set of exercises, it says, use logarithms to solve each equation. So for part A, we have that 2 to the power of x is equal to 10. So how can we solve this? Whenever we have this type of equation, the first thing we need to think about is if we can equate the bases, right? If we can obtain the same bases. But in this case, you clearly see that we cannot convert 10 to 2 to the power of something. So we cannot apply that concept, which we've seen for exponential equations. So we would have to apply logarithms in order to be able to solve this. How do we do this? Well, the first thing we need to do is apply logarithms to both sides of the equation. Remember, everything I do to one side of the equation, I need to do to the other side. So we're going to apply, let me write the steps here. We're going to apply log. Okay, you could also, if you want, apply instead of logarithm, you can apply natural logarithm and the result will be the same. Okay, but whenever, I'm going to explain that later on, but whenever we don't have the number Euler's number, it's better to just work with log. So I'm going to apply log to both sides. So this is log of 2 to the power of x equals log of 10. Once I have applied a logarithm to both sides, I can start applying laws of logarithms. For example, this x, which is in the exponent, I can bring it down here in order to leave it alone, right? So that's the next step. We're going to say that x times log of 2 is equal to log of 10, right? So now, in order to solve for x, leave the x alone, we already know what to do. We need to take this log of 2 dividing to the right side, right? So this is x equals log of 10 divided by log of 2. Log of 2. Okay, so if you solve this using calculator, because the number would be something a little bit ugly, if you do this in the calculator, you should get the final answer for x, which would be, let me see, log of 10 divided by log of 2. And this is 3.32 if you round it to 3 significant figures. Okay, so this is how we solve this type of equation. You see that we need to apply the concept of logarithm in order to be able to solve this. Okay, so that's it for part A. Then if we go to part B, it says 3 to the power of 2x is equal to 20, right? So we're going to do exactly the same thing. We cannot solve this by equating the bases because we cannot convert 20 to 3 to the power of something. So I'm going to, again, apply log to both sides. Log of 3 to the power of 2x is equal to log of 20. Once I apply logarithm, I can take the exponent down. We're basically doing the same thing, right? 2x times log of 3 is equal to log of 20. So then I can say that 2x is equal to log of 20 divided by log of 3. So finally, in order to solve for x, we need to take this 2 dividing to the right side, and we're going to get that x is equal to, we could say that this is 1/2, right? If we take the 2 dividing, 1/2 times log of 20 divided by a log of 3. Log of 3. And we can solve this using calculator. We're going to say that x is equal to 1/2 times log of 20 divided by log of 3. I get an answer of 1.36. So x is equal to 1.36. So this is the result, right? Okay, so I think this is easy, right? Now let's do part C. I'm going to do part C maybe here to save some space. I'm going to separate this using a black line there. So for part C, it says 5 to the power of 1 minus 2x is equal to 50. Okay, once again, we cannot equate bases. We cannot convert 50 to 5 to the power of something, so I would have to apply the concept of logarithms. So I'm going to apply log on both sides. So we're going to say that this is log of 5 to the power of 1 minus 2x is equal to log of 50, right? And then I can take all of the exponent down using the law that we have learned in previous classes. Remember, this should be in parentheses, 1 minus 2x, because that's the whole exponent, times the log of 5 is equal to log of 50. Then I can take the log of 5 dividing to the other side, so this would be 1 minus 2x would be equal to log of 50 divided by log of 5. Log of 5. Then, to keep on solving for x, maybe I can take this to the right side and I can bring all of this to the left side in order to have a positive sign for the x. So I will rewrite this as 1 minus log of 50 over log of 5, and this is equal to positive 2x, right? So then if I take the 2 dividing to the other side, I will get the x alone, right? So I can say that this is x equals, and all of this is being multiplied by 1/2, and here we have 1 minus log of 50 minus divided by log of 5. So we can plug in all of this into our calculators and we will get a value of x, which would be, let me see, 1/2 times 1 minus log of 50 divided by log of 5. We get, as a result, negative 0.715 if we round it to 3 significant figures. So this is the value of x, okay? So this is how we apply logarithms in order to solve equations. You see that it's quite easy, right? We just need to apply log to both sides and then start applying the laws of logarithms in order to solve for x. Okay, so let's move on to the second set of exercises. It says solve for x. So we're doing the same thing. We want to find the value of x. So we need to leave the x alone. So I'm going to write the equation for 2 times 3 to the power of x equals 5 times 2 to the power of x. Okay, the first thing we need to do here is analyze if we can simplify something. I don't see that we can simplify anything here. So if we cannot simplify this and we cannot equate bases or anything like that, we will do the same thing. We're gonna apply logarithm to both sides, okay? So if we do that, we're gonna get log of 2 times 3 to the power of x is equal to log of 5 times 2 to the power of x. And you see that, what do you see here? You see that we can apply laws of logarithms. If you remember, whenever we have log of a times b, we can separate this as an addition, right? Log of a plus log of b, right? So that's exactly what we're doing here. We're going to separate the arguments here into an addition. We're going to get log of 2 plus log of 3 to the power of x. And this is equal to log of 5 plus log of 2 to the power of x. Okay, since my objective is to solve for x, that is, leave the x alone, I will bring this term, which has an x, to the left side, and I will take this term that has no x to the right side, okay? I'm reorganizing terms in order to be able to solve this. So I'm going to say that this is log of 3 to the power of x minus log of 2 to the power of x, and this should be equal to log of 5 minus log of 2, right? If we reorganize terms. Then, by applying the third law, which allows me to take the exponent down, I can say that, I'm going to write that here. If I have log of, and say a to the power of x, this is the same as saying x times log of a. So that's exactly what I'm going to do here. This would be equal to x times log of 3 minus x times log of 2 and this must be equal to log of 5 minus log of 2, right? So here you can see that I have a common factor of x, right? I can take out a common factor, GCF, of x, and we will have log of 3 minus log of 2 remaining, and this remains the same, log of 5 minus log of 2. Finally, in order to solve for x, the only thing I need to do is take all of this, dividing to the right side, and I will have the value of x. So x is equal to log of 5 minus log of 2, and this is being divided by log of 3 minus log of 2. And I can do all of this in the calculator, and we will get the result. So this would be equal to log of 5 minus log of 2 divided by log of 3 minus log of 2. You can try doing this in your calculators to practice. So I get, if we round this to three significant figures, 2.26. This would be the value of x for this equation. Okay, now let's go to part B. In part B, okay, let me copy the exercise for it. It says e to the power of 2x minus 3 times e to the power of x plus 2 is equal to 0. Okay, I see something interesting here. The first thing I see is that we cannot apply logarithms directly in this exercise because we have the addition of different terms, right? We cannot do as we did here, where the terms were being multiplied by each other, because the terms are being added or subtracted in this case. So, as I cannot do that, I will need to see something different, okay? From experience, I already see what we should do in this case. This is a case of a quadratic equation, okay? Let me do a little change, a variable change for you to be able to notice this. I see that here we have e to the power of 2x, and I see that here we have e to the power of x. So what if I redefine the variable e to the power of x as y? I'm going to call e to the power of x is y, right? And before actually doing that, I'm going to do here something. I'm going to say that this is the same as saying e to the power of x squared minus 3 times e to the power of x plus 2 is equal to 0. I can do this, right? Because the properties of exponents allow me to do that. If I have an exponent to the power of another exponent, I can join them by multiplying the exponents, which is what we had in the original exercise. So now that you have it in this format, maybe it's easy to visualize why I decide to rename the variable e to the power of x, rename it to y. Because if I do that, I can rewrite this expression as y squared minus 3 times y plus 2 is equal to 0. And this is a quadratic equation which is easy to solve, right? Because we can just apply case 5, which is multiply add, right? A pair of values that multiplied would give me positive 2, and that added would give me negative 3. Though that pair of values in this case is negative 2 and negative 1, right? So I will get that y is equal to 2, and that y is also equal to 1. We have two possible values. But remember, this is not the answer yet, because y is not our variable. We want to find the value of x, right? So if we go back to our original variable, y is defined as e to the power of x. So we're going to say that e to the power of x is equal to 2, right? I'm going to take this a little bit down there. So if I have this situation, then I can solve for x. And in this case, I will have to apply a logarithm in order to be able to find the value of x. In this particular situation where we have the e, it's better if we use, it's better, just a second. it's better if we use here. Instead of log, we're gonna use ln, natural logarithm. Why? Because we have the number actually e. Whenever we see the number e, it's better to work with natural logarithm, because remember, the implicit base of a natural logarithm is always e. Okay, so that's exactly what we're gonna do. We're gonna apply natural logarithm. So we're gonna get that natural logarithm of e to the power of x is equal to natural logarithm of 2. So if we apply, we would need to take this a little bit. I'm gonna put it here and then I'm gonna work with that. Or actually, it's better. No, I'm gonna leave it like that. So here we can see that we can take down the exponent x and bring it to the front. This would be x times natural logarithm of e is equal to natural logarithm of 2. And if you remember from previous videos, the natural logarithm of e is always equal to 1. Natural logarithm of e is always equal to 1. Why is that? Because the natural logarithm has an implicit base of e, and if the argument is the same as the base, this is always equal to 1, okay? So all of this term cancels, and it's actually equal to 1. So there we get the value of x. X is equal to natural logarithm of 2. And this is one possible result for this exercise. But remember, we had another possibility, which is y equals 1. So we're going to do exactly the same thing. We're going to take this down here and say that e to the power of x, which is y, can also take the value 1. So if we do the same thing, if we apply natural logarithm, we're going to have that natural logarithm of e to the power of x is equal to natural logarithm of 1. So x times natural logarithm of e is equal to natural logarithm of 1. But if you remember, any natural logarithm, if the argument of a logarithm or a natural logarithm is 1, then the result will always be 0. That's another property of logarithms, right? So this term is actually 0. And we already know that natural logarithm of e is equal to 1, right? So there we get the second value of x, which is x equals 0. So these are our two possible solutions. Either x is equal to natural logarithm of 2 or x is equal to 0. Those are the solutions to part B, to this one over here. Okay, I hope that was clear. Now let's do one last example, which is a real life application of logarithms, okay? It says the radius r centimeters of a fungus on a tree can be modeled, and this is the equation of how the radius of the fungus varies. If you imagine a fungus, you know that its radius increases through time, right? So where t is the time in days since the fungus was first observed. So part A. State the radius of the fungus when it was first observed. If t is the time in days since the fungus was first observed, when it was first observed, we are referring to first observed means time is equal to 0, right? So for part A, we're going to calculate the radius of the fungus for t equal to 0. So 5 times 2.4 to the power of k times 0, okay? Any number to the power of 0 is always equal to 1. So the radius, the initial radius, is equal to 5 times 1, which is 5 centimeters. This is the initial radius of the fungus. Okay, then we have part B, which says after 4 days, the radius is 8 centimeters. Find the value of k. So 4 days, this is our value of t. This is t. And we know the value of the radius, which is 8 centimeters. So that's exactly what we're going to do. We know that r of 4 is equal to 8 centimeters. So if we use the equation, we're going to say that 8 is equal to 5 times 2.4 to the power of k. We don't know the value of k. And the time is 4. Okay, so in this case, I will need to solve for k. I will need to leave the k alone. So the first thing I see I can do is I can take this 5 dividing to the left side. So this would be 8 over 5. 8 over 5 is equal to 2.4 to the power 2.4 to the power of 4k, right? 4k. 8 divided by 5, that's a 1.6. I can leave this as 1.6. Is 2.4 to the power of 4k. Okay, so if I wanna solve for k, in this case I will have to apply logarithms. Okay, so that's exactly what I'm gonna do in order to leave the k alone. So apply logarithm to both sides. If I apply logarithm to both sides, we're gonna get log. We're gonna get log of 1.6 is equal to logarithm of 2.4 to the power of 4k. Once I have applied logarithms, I can take all of the exponent to the front, right? Applying the third law of logarithm. So log of 1.6 is equal to 4k times logarithm of 2.4. I don't need to write the parentheses here anymore. There. So the next step would be to take all of this dividing to the left side, right? So log of 1.6 divided by log of 2.4 is equal to 4k. And finally, to finish leaving the k alone, I will take the 4 dividing to the left side. So k, or I'm going to write it like this, 1/4 of log of 1.6 divided by log of 2.4 is equal to k. And then I will use calculator in order to determine the value of k. So this is 1/4 times log of 1.6 divided by log of 2.4. 2.4. And I get a value of k which is equal to 0.134 if I round it to 3 significant figures. So that's the value of k that we're being asked for part B of the exercise. Finally, find the value of k, yes. So finally for part C, it says calculate how long it will take for the radius of the fungus to be 10 centimeters. So for part C, 10 centimeters, that would be the radius, right? So this is a radius. So we're gonna set all of the equation to equal to 10, right? 10 is equal to 5 times 2.4 to the power of, we already have the value of k, we cannot use that value because it's a constant value. So to the power of 0.134 time, right? We don't know the time, times t. So in this case, we need to solve for t, and the process is exactly the same. We're going to need to apply logarithm in order to solve for t. The first thing I'm going to do is take the 5 dividing here. 10 divided by 5, that's 2. So 2 is equal to 2.4 to the power of 0.134 t. Then I will apply logarithm, apply log to both sides. So this would be log of 2 is equal to log, and if I'm gonna make this a little bit faster, I'm gonna write it like this already, taking the exponent down, times log of 2.4. So finally, if I solve for t, I'm gonna assume that you already understand what I'm gonna do here. The value of t would be equal to 1 over 0.134 times log of 2 divided by log of 2.4. That's all we need to do in order to solve for t. If we do this in the calculator, we will get the final answer, which is time equals 1 over 0.134 times log of 2 divided by log of 2.4. And I get a value of 5.91 or 5.91 if we round it to 3 significant figures. So we're talking about t is in days, right? Yes, time in days. So after 5.91 days, the fungus will double its initial radius, right? From having an initial radius of 5 centimeters, after 5.91 days, it will have a radius of 10 centimeters, okay? So that's it. I hope this was clear for you people. If not, please let me know and we'll clear doubts in future live sessions. And we're going to be practicing a lot with exercises about this later on, okay? Thank you for your attention and see you.